Reactivity of aldehydes and ketones. The carbonyl group is in general polar. Where the oxygen is electronegative, it's going to build a partial negative charge on it. And the carbon is going to be electron deficient and it's going to be having a partial positive charge on it. And because of this partial positive charge on carbon, a nucleophile can go and attack this carbonyl carbon. Aldehydes are more reactive than ketones and can be readily attacked by a nucleophile. And this is because of two main reasons. The first reason is the electronic reason. Aldehyde in general is going to have a greater partial positive charge on its carbonyl carbon than a ketone. Now let's compare the structure of aldehyde with that of ketone. Now in aldehyde, we do have at least one hydrogen, whereas in ketone, we do have two alkyl groups. Now the nature of the hydrogen is to withdraw the electrons. So hydrogen withdraws electrons. Whereas the nature of an alkyl group is to donate the electrons. Now, if you want the nucleophile to attack each one of these carbons, you definitely need to have the partial positive charge on this carbon. When you have an hydrogen, it's definitely going to withdraw the electrons, meaning that this positive charge is going to get increased, right? Let's say that you have more positive charge on this carbon. Now, in the case of ketone, you do have alkyl groups. You do have only alkyl groups. The alkyl groups in general is going to donate the electrons towards the carbonyl carbon, right? So which means the partial positive charge is going to be decreased. So now let's say which one of these will be attacked by the nucleophile readily. Obviously, the nucleophile is negatively charged, right? So, and it will go and attack the one where you have more concentrated positive charge. So it will go and attack this carbon, right? So aldehydes are more reactive than ketones. Now let's compare the structure of formaldehyde with a normal aldehyde. So in the case of formaldehyde, you do have two hydrogens, which means the electron withdrawing abilities of these hydrogens are going to be more. And therefore, this carbon is even more electropositive, right? So I'm going to put more positive charges on this carbon. And therefore, between these two, which one of this is going to be more reactive towards a nucleophile? Obviously, this one has got more electropositive charge, and therefore a nucleophile will go and attack this one more readily than an aldehyde. And therefore, the relative reactivities of the aldehydes with the ketones is going to follow this order, where the formaldehyde is more reactive, and then comes the normal aldehyde, and then finally the ketone. The second reason is the steric reason, steric hindrance. How aldehydes and ketones are affected by steric hindrance. In general, ketones have greater steric crowding than aldehyde. This can be seen from the structure. So let's compare the structure of aldehyde with ketone. So aldehyde have at least one hydrogen, whereas ketones have two alkyl groups, and because of which we can definitely say that the ketones have greater steric crowding. Now, if you want to make the nucleophile to go and attack this carbon, which of these carbons is easily accessible? Obviously, the carbonyl carbon in the aldehyde is easily accessible because you only have an hydrogen which is going to take less space. Also, the transition state that is obtained in the case of ketones when they are attacked by nucleophile is going to be really crowded because of the two R groups, and therefore this is going to be unstable. Relatively unstable. And for this reason, we can definitely say that the aldehydes are more reactive than ketones. Now also, when the ketones are going to have larger R groups, it's going to be even less reactive. So here is an example. So here we have three ketones and they vary in their bulkiness of the R groups. So here you have more bulky R groups. With the presence of more bulky R groups, you can see that the reactivity towards the nucleophile has decreased. While this is more reactive, this one is less reactive. Here is the relative reactivities of the different carbonyl compounds, and we have talked about acyl halides, acid anhydrides, ester, carboxylic acid, amides, and carboxylate ion before in the chapter carboxylic acid derivatives. Now we have included aldehydes and ketones. Aldehydes and ketones are in general more reactive than ester, carboxylic acid, amides, and carboxylate ion, but they are less reactive than acyl halides and acid anhydrides. We have seen that the carboxylic acid derivatives undergoes nucleophilic addition elimination reaction. Here in this case, the nucleophile goes and attacks this carbonyl carbon, thrusts these electrons towards oxygen to form the tetrahedral intermediate. And this tetrahedral intermediate will collapse to either eliminate Z or Y. But if Z is going to be a strong base, it would be Y's turn to get eliminated when these electrons come in, so as to produce a new compound. In the case of aldehydes and ketones, what it forms is the addition product. Let's see how. So in the case of aldehydes and ketones, we do not have any leaving group, or in other words, these groups are strongly basic and are not ready to leave from the system. And therefore, when the nucleophile comes in, it simply gets added to the carbonyl carbon, right? So the Z will go and attack this carbonyl carbon and thrust these electrons onto oxygen. Okay, it now forms the tetrahedral intermediate, which is going to look like this. And in the next step, this oxygen is going to get protonated. This oxygen with a negative charge is going to get protonated, and it will form the addition product. But if Z is going to be an electronegative atom, such as oxygen or nitrogen, which has lone pairs of electrons around it, it can undergo nucleophilic addition elimination reaction. But before that, there should be enough proton in the reaction where this oxygen will get protonated first. Okay, let's say that this oxygen is going to get protonated. Okay, so it will go and grab this hydrogen and it will be protonated. And the Z will donate its lone pair of electrons to form a double bond here, kicking off the water molecule here. So now this reaction can be called as nucleophilic addition elimination reaction, because as the Z gets added to the carbonyl carbon, the water molecule is getting eliminated. Now it's important to see the difference between the nucleophilic addition elimination reaction of aldehydes and ketones with the nucleophilic addition reaction of the carboxylic acid derivatives. Here, in carboxylic acid derivatives, the group that is leaving from the system is the one that is directly attached to the acyl group. So this is the acyl group, and Y is getting eliminated. But here, in the case of aldehydes and ketones, the group that is getting eliminated is water. So that is the main difference between these two nucleophilic addition elimination reactions. Remember, the nucleophilic addition elimination in aldehydes and ketones only happen if there is enough proton present in the solution, and also the Z needs to have lone pair of electrons present on it to form a double bond.